Good afternoon, everybody. My name is Valentine, and I'm happy to share my research topic today with you, which is artificial neural networks in computational fluid dynamics. And I would like to guide you through this agenda real quick. So I want to say something real quick about computational fluid dynamics, what it is, and link it to the research topic. Next, I'm going to talk about the data that we have used and processed, the method that we have been used, and lastly also share some of the results and findings that we had during the study. So let's start with fluid dynamics at first. Say when there's an engineer tasked with the development of a new product, such as an airplane wing or a car windshield, aerodynamics plays a very important role in the overall design process, right? So because an airplane wing is basically an airplane is supposed to fly without being tested experimentally on the engineer's own body, so it has to be functioning. And fluid dynamics help us to create, measure, and also test the flow of these fluids without actually building a prototype in the real world. So this is where also then computational fluid dynamics allows us to generate accurate solutions for physical phenomena and apply them then to the development of new products. And fluids are all around us. So we drive, we fly, we breathe, we use fluids daily. And in fact, every one of us has products at home that are designed with the help of fluid dynamics. So say this is your sink in your kitchen, the dishwasher, the fridge, the heating system in your house, the water system, the shower, the oven, what else, a microwave, so on and so forth. So there are a lot of tools and gadgets in your household which are actually designed through the helps of computational fluid dynamics. However, the biggest pain point is, though, that CFD requires a lot of hardware resources. It's expensive in time because it consumes a lot of time. Sometimes even weeks are used for the simulation. So as we know, when something is expensive in hardware resources and time, it's not really practical, but still it is a required thing. So the objective of the study is that we try to understand whether machine learning can be used to create such simulations for us instead of the numerical simulations that are nowadays used. So the data set that we've been using is coming from two test cases. So one case is the cylinder case and another case is the SAE body. Both of them are coming from 3D space. So we have a 3D model of the cylinder, roughly 300,000 cells. And we already see that the flow structure behind the object is very periodic and very smooth in its flow structure and also symmetric in Z coordinate. However, on the SAE body, which is a more realistic use case from the aerodynamics field, we see that there's a highly chaotic flow structure after the object. So it should mimic a car, kind of like a low resolution car. But we can see that the flow structure after the object is just like there are a lot of turbulences. We cannot really identify any pattern in here. So we already see that these two cases are very different from each other and are giving us a nice ground to introduce machine learning to them. So let's talk about the method real quick. Imagine a flow field like a picture that evolves over time. So it's like the pixels in a movie, right? But these points in the flow field can represent high degrees of freedom, which is very unsuitable for machine learning. So hence we use the POD, the proper orthogonal decomposition, which is a tool coming from the linear algebra. And it uses the singular value decomposition technique to decompose such flow fields that might have high degrees of freedom, especially in the 3D space. And as a result, we receive something which is called the POD modes. And these modes are, in fact, just the eigenflow fields that are very static in space. And it's just a mixture, actually, of these eigenflow fields that change then over time. So in return, what we can do is we can describe the evolution of a flow field via these temporal coefficients. So think of it again as a picture, and the coefficients tell us then how does the picture change over time. And during the processing task, so we use the cylinder case, we have exported roughly 250 snapshots of the flow field, used it for the POD, have received 30 modes and 30 coefficients of a sequence length of 250. And for the SAE case, it has been roughly 200 snapshots, and we've received 100 modes and 100 coefficients. So as we can see, for the SAE case, much more data was available and much more coefficients have been produced through the POD. And the general approach was that since we're dealing with time series data here, so after decomposing the flow field, we learned the LSTM model based on these coefficients and try to predict the future value of these coefficients. And then with these predicted values, rebuild the whole flow field. So in theory, we should have been able to build a model that predicts future coefficient values. And with these values, we can rebuild the whole entire 3D flow field. When we have a short look at how these coefficients look like, so in the cylinder case, and also as we've seen previously, the structure is very smooth, so low frequency in the earlier ranks on the left-hand side with nice smooth curvatures, but also higher frequency on the higher ranks, like as we can see on the right-hand side. So what we can see and identify is here, a lot of patterns are in there, which might be a great easy task for machine learning models to comprehend, to understand, and reproduce. When we have a look at the SAE body and what we have expected before, the coefficients are much more chaotic. So there's a lot of turbulence in here. We see that the early ranks, there's a lot of randomness when there's the curves here and there just appearing with lower frequency in the early ranks, but a lot of high frequency turns and curvatures in the higher ranks. So it appears to me, like personally, we're just looking at them, there's no real pattern to follow, to find. So it's just a lot of noise that is in here. Now, from a model's perspective, so we've used a multi-layered LSTM structure with most of the layers containing 250 units. And after the second LSTM layer, there was a dropout included of 20% to mitigate the risk of overfitting, and then followed by 3 dense layers to guide the model, so to say, to create a single final predicted value for each of the coefficients. On the data side, though, we specify the lag value of 20. So the lag value is, so to say, the number of historic values which are used to create a prediction. And with that, we have used 20 historic values to create a prediction. And on the training side, we have an epoch rate of roughly 400 to 500 has given us the best results with a batch size of 1,024 and a very low learning rate with even weight decay included. And as a loss function, we applied mean absolute error. So this model strategy has been found by an optimization process and has given us the best results. Having a short view on the results for the cylinder case, we can see that the model is doing a great job in finding the exact value for a future value on these coefficients. So especially in the low rank on the left image, we can see it's following exactly the ground truth of this coefficient. And also on the right image, where there's a higher frequency included, we see that it can differ between low and high frequency, although it's only one model. So we do not imply multiple models here. It's just a single model, which can differ between low frequency and high frequency. And with that, also basically nail each predicted coefficient. However, to estimate the true error rate, we had to rebuild the whole flow field and do a pointwise analysis, which is quite a very complex process to do. So for this study, we only compared the true predicted, the ground truth of the coefficients with the predicted coefficients, and received a roughly percentage predictive error of 0.002, which is like really low. So the model, as we can see here, is doing a great job in following and understanding the curvatures for the cylinder case. But when we have a look at the SAE body, though, we see that the model struggles sometimes to find the accurate value for the coefficients, especially like when it's of higher frequency and when there's a lot of randomness included. The model tries to find it, so there's a trend which is like somehow correct, but the actual values are off. So since we're dealing with very low numbers in computational fluid dynamics, we have to be accurate. Otherwise, it's not giving us any value. And again, here we compared the ground truth of the coefficients with the predicted values and received something like 0.73% error rate. So what we already can see here by this short study is that an LSTM model struggles to follow the complex flow structure of a more realistic case, so it's the SAE body, but has doing a great job when it comes to the cylinder case, which is, well, yeah, a rather easy task, I'd say. So to conclude, what we've seen here and the learnings is, so I think, or we think, that we've identified that the LSTM model is not so really suitable for steady, is really suitable for steady and periodic flow structures, so AKA the cylinder case, but it's not so suitable for transient cases that includes many turbulences, so the SAE body. And for real world applications, we do think that LSTM models are not yet fully, or cannot really yet fully support numerical methods. And also we think that it seems to be that LSTM models are too immature yet to provide a real advantage for solving CFD simulations. It's just because the error rate is just too high. So an error rate of 0.7 is too high for a real world application, because we do not want to introduce more error than we can actually solve per iteration. So it's unfortunately cannot provide us any benefits here. And another learning was on the POD side, that to build the POD, so to decompose a flow field, it already takes a lot of time to compute. So an engineer who is using the POD has to factor these in, that to compute the POD takes a lot of time. And on the right-hand side, this is where we made an attempt to compare the original flow field, like the real flow field, with the predicted flow field, where we recomputed the flow field based on the predicted values. And what we have created here is a heat map, just giving us the delta between the original values and the predicted values. And the higher the value, so the higher the delta, the higher the difference, the higher the error, the more it shifts toward red, and the lower the delta, the lower the error rate, the more it shifts towards blue. And what we see is that right behind the object, there's a lot of red, and especially in this crucial area after the model, it should actually be that this is the most crucial part for the whole simulation. And since we're doing a lot of errors here, introducing a lot of errors here, we see that the LSTM model might not be suitable in total for supporting numerical solvers during this process. So with that said, it was a pleasure to present this research topic to you, and I'm happy to discuss now your questions. Please feel free to reach out to me anytime, or I'm also happy to connect on LinkedIn anytime, so I'm happy to answer your questions now.